This problem gives us this function, a quadratic function f, that is written in this way. So notice that this matrix, we can always rewrite it into a symmetric one, just to keep the same value of this. Okay, so the first question is to find the directional derivative of this function f at point 0, 1 and in the direction of 1, 0. So this is already a normalized vector, it's a unit vector already. Okay, so we can just directly compute the inner product of the gradient of f at this point and this vector. And the second question is to find all the points that satisfy the first order necessary condition, and then want to check if f has a minimizer, and if it has a minimizer, we need to find them. If not, we need to explain why. Okay, so the first step is to convert this quadratic function into the standard form, where we want to have, so here this is like x transpose ax, but we want to rewrite it as 1/2 times x transpose qx, where q is a symmetric matrix. So to that end, we just need to take the sum of a and its transpose. That's our q. So a and a transpose, so this is the a and a transpose gives us this. And then we'll get the standard form of the quadratic function f of x, and that is half x transpose qx. So notice that q is symmetric now, and the other terms are the same. Okay, so for this quadratic function, we know that the gradient is just qx plus b. Okay, and this is the q, this is the b. I think in the standard form we may also have a minus x transpose b. Then in that case, the gradient will be just qx minus b. Okay. Just notice that whatever you multiply to x here, it should be the b. Okay, so the directional derivative, as we said, just the gradient of f at the point 0, 1 times the given direction, which is 1, 0. So take the inner product of the two. So just evaluate them. The gradient of f at 0, 1 is just plug in 0, 1 here, and that is this. And the 1, 0 is here. Then take the inner product. Okay, and the next step is to show to find all the minimizers. Since this problem is unconstrained, so the first order necessary condition is the gradient equals 0. And by that, we need to solve that qx plus b equals 0 for x, and that gives us only 1 point here. Okay, and because this is the only point that satisfies the first order necessary condition, we need to check if this is going to be a local minimizer or not. If it's a local minimizer, we need to make sure that the second order necessary condition also holds. But that means the Hessian needs to be positive semi-definite. So let's check. This is the Hessian matrix, which is just a Q. And the determinant of this matrix is -8, which is negative. So it has the determinant of this matrix is negative, and this is 4. That means this matrix is it has two eigenvalues with the different signs, so they are not both non-negative. And in this case, we know that the Hessian matrix is not positive semi-definite, and that means this point cannot be a local minimizer. Okay, and it cannot be a global minimizer for sure, right? Because a global minimizer must be a local minimizer as well. So the f does not have any minimizer.